Okay, here we're going to calculate the electric field due to a ring of charge. This is one of my favorite problems. It's also a very complicated problem, and there's a very steep learning curve here. So take very good notes from this video. So I've got this ring of charge that rings around the x-axis. Here's my x-axis. Here's the y-axis. The x-axis is the axis of symmetry. It comes right through the center of that ring. So that ring is coming out like this, and the x-axis is going right through the middle of it. The total amount of charge on the ring is Q, and the radius of the ring is A. We're going to find the electric field due to that charge distribution out here at a point X straight along the x-axis. This problem is going to be nasty, but at least it's possible. We can't find the electric field, say, at this point right here or this point right here. That's an incredibly difficult problem. So this is a simplified version. We're only finding the electric field along the axis of symmetry. And we're going to do this by building a Riemann sum. We're going to use a bunch of calculus. So we're going to divide this whole thing up. Think back to Calc 1 with Riemann sums. We're going to divide this whole thing up into, say, n equal segments. Each one that's a little delta s, think arc length s, long. So in there I've got a little bit of charge. We'll call that delta q in that little bit of segment there, that little bit of arc. Now my total charge density, I've got Q all the way around. The total circumference is 2 pi A. So the charge density, the charge per unit length, is total charge divided by total length, Q over circumference. So the amount of charge that's in this little segment right here, delta Q, will be the density times the length. That's charge per unit length. That's length. So the amount of my total charge, Q, that lives in this little section here is the total divided by the total length times delta S. That's the key to the whole problem right there. Okay, we're going to treat that little delta Q there as a point charge. We're going to pretend that delta S is small enough that all of that charge is concentrated at a single point out here. And then when we take the limit as delta S goes to 0, that becomes an okay approximation. So out here at point X, the electric field from this point charge, so to speak, will point directly away from it. Remember, electric field points away from positive charges. In my charge here, we're assuming Q is positive. So that will create some E vector down here, just from that little contribution right there. Every little slice here is going to create a different E. This little slice down here will create an E that points up that way. This slice here will point an E that points straight away from it. So we're going to add all those up as we go around the ring. But this particular slice we're looking at gives us an E vector that points down. Now these are vectors. To add up vectors, we have to add component-wise. So we got to figure out the X and Y components of E. Well, first I'm going to make the argument that all of the Y components all the way around all add up to 0. So this little one we're looking at here, E points down this way and his Y component is here. There's a corresponding spot down here whose E vector would point up, and that Y component would cancel out this Y component. All the Y components, when we go around the ring, all the Y's add up to 0. So my EY all the way around is 0. So the only thing that's left over, the net electric field, will point in the X direction. Remember, we always have to do these component-wise. I can never write a Riemann sum about E. I need a Riemann sum for EX and one for EY. So EX. EX, well, we're just going to use trig here. If I've got this angle, we called it theta here. This will also be theta here. Those are vertical angles. EX we're going to get using cosine. So if this is angle theta, EX will be the magnitude of the vector times the cosine of theta. R here, my distance, is just square root of x squared plus a squared, Pythagorean, here in this right triangle. Total E is just k times charge over distance squared. That's Coulomb's law for an electric field. K times the amount of charge. Notice this is approximate because this charge is a little spread out, but when we take the limit as delta S goes to 0, this becomes closer, and in fact goes to equals. So the magnitude of the vector is approximately k delta q over r squared. It's EX we're after. Okay, so as we said, all the EYs add up to 0. EX, from that one little charge we're looking at here, is approximately, I called it the ith one, is approximately the magnitude times the cosine of theta. Cosine of theta we can actually write using parameters we already have. If we look at our right triangle here, cosine of theta will be adjacent over hypotenuse, x over r. Remember, r was square root of x squared plus a squared. So the electric field in the x direction from that one little slice of charge is approximately this. We know what magnitude of E is. We said that just a minute ago. That was k amount of charge over r squared. Look back in the video. We know what delta Q is. That was Q over 2 pi a times delta S. Okay, so we get the ith component of our electric field in the x direction. This is the amount of electric field in the x direction from that one little tiny slice of charge is approximately, this should say approximately, this amount. So then the total in the x direction, we build a Riemann sum. So this is a Riemann sum. We add all these up. So I just put a sum in front of that. And now we do our calculus. We take the limit as delta S goes to 0. That's the same thing as n going to infinity. This Greek letter sigma becomes a stretched out S in the limit. Delta S in the limit becomes a ds. And then we put in our limits of integration. So we're integrating around a ring here. So our variable of integration here is S, arc length. And that goes from 0 to the total arc length, circumference, 2 pi s, 2 pi a. So we get this integral. And you look at that and you think, oh my God, that looks terrible. But it's actually very easy because my variable of integration is S and there are no s's in the integrand. These are all constants as far as s is concerned. All of this comes outside the integral. And I get the integral from 0 to 2 pi a of ds, integral around the circle. That's all we're doing. We're integrating arc length around the circle. The antiderivative of ds is just s, and then evaluated from 0 to 2 pi a. So we just get a 2 pi a. All of this came out. The 2 pi a's cancel, and we get this expression. That is the total electric field and at all points in the x direction. So if we wanted to write it as a vector, we could say E as a vector equals kqx over x squared plus a squared to the 3/2, comma, 0, because all the y's going around the circle canceled out. Notice, by the way, that we ended up with this 3/2 power in the integrand. That's very common. That's going to happen on probably 80% of these kinds of problems. Okay, now let's look at some limiting behavior. So we've got this ring here. What happens if we're really, really far away from the ring? What happens is we're thinking is the limit as x goes to infinity, but that's really not what we're doing. In physics, we'll write stuff like this. In a math class, we would say limit as x goes to infinity. But here, we're going to consider what happens when x is much, much bigger than a. When you write greater than twice, that means not just bigger, but much bigger. Okay, so this is the expression we just got. I just recopied it over, no math happened there. I want x to get really, really big. So what we're going to do is, in the bottom here, we're going to factor out an x from this expression on the bottom, this radical. Okay, so some math magic's about to happen here. So take your time with this. I'm going to pull an x squared out here by dividing both of these by x squared. So x squared divided by x squared is 1. A squared divided by x squared is a over x squared. So I factored out the x squared. Then when I take the limit, if x is much, much bigger than a, or just think limit as x goes to infinity, this thing goes to 0. So I just get x squared times 1 raised to the 3/2 power. Well, the half and the square cancel, and I get x cubed. That cancels one of the x's on top, and we get this. So in the limit, as x gets further and further away from the ring, my end behavior, so to speak, is that the electric field will look like kq over distance squared. So I've got some ring, and I'm really, really far. I'm way out here, far away from it. That's Coulomb's law for a point charge. So if you're really far away from a ring of charge, it looks a lot like a point charge.